Please, everybody should mute. I'm trying to mute everybody. Everybody should mute, please, because people are coughing from their background. Please mute yourself. It's only when you want to ask question, you unmute yourself, please, or you want to respond, you unmute yourself. Unmute yourself so that it doesn't distract other people, please. So I think we'll start. We have been discussing last Thursday. We started our discussion on logistic regression, and because logistic regression, the way it is not as straightforward for people to understand like linear regression. So most of the talk there are abstract. I'm trying as much as possible to make people to be able to conceptualize, to downplay on the abstract parts and make you to, for you to understand, what you actually need to understand. And the funniest thing is that once you understand it, the output is easier to interpret than that of linear regression. Though the concept initially may be difficult for people to grasp, but once you grasp it, you discover that the output is easier to interpret than that of linear regression. And that is why today, being the second one, the second one, I can't say it's the last, the second lecture on the linear regression, because it started on Thursday. I want us to know, I just want to pin down on few things that will make you to understand how even the logistic regression, how you can even use and to solve it to a certain extent. Then when you run it with SPSS, the way the output look like and the way you interpret. And that is why what I want us to dwell on today. If you remember, we said that is in class of what we call generalized linear model, in the sense that generalized is normally it's not part of linear model, because those ones that are under linear model, they are called general linear model. Those ones, the output, the outcome variable is continuous, or the outcome variable for them are continuous. And once the outcome variable is continuous, you can say sometimes it may follow normal distribution, so you can actually predict the actual value. Actual value, something like when you say continuous blood sugar. With linear regression, you can predict the blood sugar. But for logistic regression, because the outcome variable is not the actual, what you get eventually is categorical. Like now, even if you are talking of blood sugar now, you might have said, oh, diabetic, not diabetic. Diabetic, not diabetic, two categories, and one is 1 and the other one is 0. If diabetic is there, it's yes, that is 1. If it is not there, it's no, that is 0. So you see that that one, it is difficult to plot to know, because that body cannot follow normal distribution. So you just have to use a transformation method to make it look as if it follows a linear model. And when you put in the transformation, and the transformation they use in logistic regression is logit, which we have explained last week, that logit just means the logarithm of odds. You know that if you want to predict something, it's either yes or no, there or not there, 1 or 2, 1 or 0. It's probabilistic. So the probability, if it is there, is 1. That is certain. If it's not there, it's 0. And you know that probability is in between 0 and 1. But what it does is still probability, but it's binomial. It's a form of binomial distribution in the sense that it is only two outcomes. Instead of you having some outcome, even between 0 to 100. but it become only 0 and 1 or 0 and 100 because 100 mean 1. In probability, 100 mean 1. If you want to change from 1 to 100, you multiply by 100. If you want to change back, you divide by 100. Like 20% mean is 0.2. That's what I mean. So when we say probability is from 0 to 1, if you want to put in the percentage from 0 to 100%. So the logistic regression, because it's either there or not there. So that limitation, to overcome it, you know, people now, intelligent people now, okay, let's transform it. When we transform it from probability, you now calculate odds. No, probability is risk. So, and odd is probability over 1 minus probability. So if you want to change anything from probability to odd, you put the probability over 1 minus the probability. It gives you the odd. If you calculate it, now find the logarithm of that odd. That is the logic, and that is the transformation they did for logistic regression. So that transformation is the link function now. The log odd is the link function, and that is all those models that are not linear model. They are not under general linear model, but because you made them linear by putting a link function, like example is this log odd. So we now call them generalized linear model. That is, it's an extension of linear model that accommodate those things that will not have followed normal distribution, but they will now do as if they follow normal distribution. By the time you introduce a link, you transform them through a link. That is just the summary. So when you do that, the equation is what you now see here. You are seeing here. The equation is, if you remember, in the normal linear model, in the linear regression, the equation is y is equal to this alpha plus beta x. That's the linear equation. Why this alpha you are seeing, it can be written as beta 0 also, it doesn't matter. Beta 0 or alpha, then beta x. That beta doesn't have, since it doesn't, beta 0 or the alpha, doesn't have x because it doesn't have, what do I call it? A variable attached to that is a constant. That is the value of y when s is equal to 0. Why the beta that has the x is the regression coefficient of the x of that variable. That is the change in the value of the y per unit change in the value of the x. So y is supposed to be on the right side if it were to be linear. Just a minute. So now you will see that y is supposed to be on the right side, but because it's a link function, you cannot use y directly. What represents y is that natural logarithm of odd. Natural logarithm of odd, which is the log odd. So that's natural ln is natural logarithm. P over 1 minus p is odd. That is probability over 1 minus probability. Because what you have with you is probability of, like for example, the example we have here now, the outcome variable here is cardiovascular disease. Maybe we'll look at it because I want you to be able to conceptualize it. So example on this 2 by 2 contingency table is that we have 1,000 people. Out of the 1,000 people, you will see that 300 are obese. Can you see? 1,000 people. Out of the 1,300 are obese, and 700 are not obese. So making 1,000. So out of the same 1,000 people, 106 have cardiovascular disease, and the remaining 894 do not have cardiovascular disease, making 1,000. So if you look at it, that 1,000 is at the corner. If you look at it from the angle of the exposure, how many are exposed? 300 are exposed, 700 are not exposed. That is obese, not obese. If you look at it from the angle of the people that have cardiovascular disease, 106 have cardiovascular disease, 894 do not have cardiovascular disease. Equal that to 1,000. So the only thing is that along the road, the obese, not obese, is the exposure, is the independent variable, and the outcome variable is the cardiovascular disease. That is, we want to see if obesity contributes to cardiovascular disease. It's not the other way. So your cardiovascular disease cannot be a risk factor to obesity. So obesity is that a risk factor to cardiovascular disease. So if you look at it from that angle, you understand this table now, you will see that 46 people among those 300 that are obese, they have cardiovascular disease, while the remaining 254 do not have cardiovascular disease. 60 among the 700 who are not obese have cardiovascular disease, while the remaining 640 do not have cardiovascular disease. And when you look at it critically, you will see that when you now come here now, when we talk about, instead of putting y, we put p over logarithm of odd. So what is representing the y, which is cardiovascular disease here, is what's represented here will be the probability, because here is not the value you are talking of. You are talking either yes or no. Cardiovascular disease, yes or no. So what we want to know is how many are in yes category, how many are in no category. So what is the probability of finding somebody and that person has cardiovascular disease, which is the P. So, but since that probability itself will not follow normal distribution like that because it's a binomial distribution. So, though it can only follow normal distribution if you take sample many times, then naturally it will not follow normal distribution because it's binomial. So you now change it to log odd. Odd of the probability is probability over 1 minus probability, and you now calculate the logarithm of odd. So that is the logic. That is the link function. So what is representing y, which is the cardiovascular disease there, is the logarithm of odd, which is log p over 1 minus p. But the other side, the right side, is the model that has the x and the intercept. It has the regression coefficient, which is beta, and the alpha here, which is Campbell. This regression coefficient, you can call it beta 1, and the alpha will be beta 0. And this example you see is just an example of simple logistic regression, as I've shown you before. If it's going to be multiple now, you're going to see that we're going to have more than one beta. We have beta 1, beta 2, beta 3. We have beta 1, beta 2, up to the number of people. Up to the number of people that, number of variable, independent variable that are there. Now, we just in a simple form now, this example we have now is one outcome variable, which is cardiovascular disease, and one exposure variable, which is obesity. And that beta 1 here now will be the x1 will be the obesity. And beta 1 will now be the regression coefficient, that is change in the value of the y per unit change in X. But actually, if it were to be linear regression, it's going to actually be change, beta here will be change the value of y per unit change in X. But here it's not actually change the value of y. In logistic regression, it's change in log odd, because what you have here, what is representing y here, is log odd. Change in the log odd, which is the logic, per unit change in X. Can you see that? So it's not changing y, it's changing log odd per unit change in X. So if you look at it, let's just apply this example we have given here now to this equation. You will see we have three scenarios we produce here now. Number one, you can first of all even know what it is if you have not even considered X. Dr. Samuel Batunde, please, I've muted you, were making noise, I muted you, and you are still making noise. And you will mute yourself. Please mute yourself. If you have question, you can shout it. So, or you wait till time we finish, you ask your question. Please mute yourself. Now, you will see now the first scenario is want to look at a situation when y is without x. That is, even if you are not considering, you can take your measurement of how many people have cardiovascular disease, how many people do have, even without even collecting data or considering data on exposure variable like obesity. So at the end of the day, in this study now, where we have 1,000 people, they were able to see that 106 have cardiovascular disease and 894 do not have cardiovascular disease. So you can predict, if you are to predict the value of y without x now, it's just the prevalence of cardiovascular disease which is 106 over 1000. Are you seeing now? 106 over 1000. Now, if that shows that because we know that the beta 0 is the alpha, is the value of y when x is equal to 0, when x is not there. So we first of all want to consider the value of y when in fact there's nothing like exposure variable, it's just y alone. And this the prevalence, what you are considering here now, is just the prevalence of the attribute of the disease or of the outcome. And it's synonymous to the mean in when we are considering, we are treating linear regression. The mean of y, no, without actually even looking at the model, y has its own mean. What the function, the mean of y is doing the same thing as what the prevalence of the y. The prevalence of y here will be 106 over 1000. So when we look at, let's look at what is the value, what is the, how can we predict even the y, even without x? And that is what you first of all have here. Because when you run it with the software also, like SPSS, it will first of all give you block 0. That's what it will give you, block 0. I will show you an example of the output. Block 0. In that block 0, it's just showing you that it's not putting that exposure variable. It's only the outcome variable is running. So look at it. If you consider you apply this equation now, y without s, in that case, y without s is the total. The total, you consider the total. You don't consider inside this one. You just consider the total. If obesity is not considered, you still know that the total that have cardiovascular disease 106 over 1000. So when you look at it now, p all over 1 minus p is 106 over 894. I don't know, some people can, it's a simple mathematics. Some people can be flagged by just because of this. Look funny, because let me just demonstrate something now, because sometimes it may be funny. You may be talking to adults, you are talking to adult, and adult learning is different from where some people, they are adults, they have left these things some years ago, and they are now coming back. So simple mathematics may look difficult to them. What if actually the prevalence of, I think you are seeing, yes, I'm showing, let me reshare that, because I'm sharing a whiteboard to be sure that you are seeing it. It's actually the prevalence of y is 106 out of 1000. As you can see there. That is P. That is the probability of having y, of cardiovascular disease. So P is 106 over 1000. Then 1 minus P, which is the probability of not having it, is the remaining one. Because the total is 1000 and 106 have cardiovascular disease. The remaining 894 do not have. So the prevalence 1 minus P will be 894 over 1000, not over 100, over 1000. Sorry. So odds, we are talking of odds now. Odds will be, we know that odd is P over 1 minus P. So that shows that from this now, it's going to be 106 over 1000 divided by 1894, rather, 894 over 1000. So if you remember change of, if you want to consider, go on 106 in mathematics over 1000 times, if you change this division to times, become 1000 over 894. So this thing now will not 1000 will cancel out 1000. And that cancel 1000. It will be 106 over 894. Can you see? So that was why we don't want to just say the log odd, just say 106 over 894. So all this is just for you to see how we get that 106 over 894. Now, if you continue our work, can you see? So now the P over 106 over 894. The logarithm, can you see, is equal to this alpha is the beta 0. The same thing as beta 0, I've said it before. So beta here is the beta 1. Because here we are considering y without x. So y x will be 0. There's nothing like x here. So the x here will be 0. When you now come here, now, if you divide the logarithm of this, I just keep this here. Logarithm, if you divide this by this, look at the way you calculate it here. Look at this table, this doing table. Y without x. The frequency 106. The frequency of no CDV is 894. If you say this over this, look at it. P over 1 minus P, 106 over 8 over 894. It gives you 0.11. Logarithm of 0.119, it will be minus 213. Can you see? That is what you have there. This is the logarithm. So since this x is 0 here, has no value, B1 will be out. B1 times 0. To be out. So that shows that B0, beta 0 is minus 2132. So what it's telling you is that the intercept, that is the value of y, when s is not there. That is when there's no, you are not even considering any exposure variable, is this. And it's very funny. This, if you look at it, is like you say 106 over 89, it give you 0.119. If you now do later, you're going to see that we do anti-log of it. It will still go back to 0.119. Anti-logarithm of it. You're going to look at it. See. Okay. Now let's now come to scenario 2 now. When you now have x, this is the block 1 now. Because when you see, you're going to see it in the SPSS output, you're going to see block 0, block 1. We have finished with block 0 now. Block 1 now, when you have x, that is when you have an outcome variable, let's say example now, obesity is there now. Of course, the obesity, we are considering obesity. Obesity, yes or no. If it is no, is 0. If it is yes, is 1. So those two scenarios now. For obesity is equal to 0. You're going to see under here, when obesity is no, how many have CVD? 6 or 60. Then we don't, you that don't have 640, the total 70. Normally the probability is 60 over 700. But we are looking at the odds. So if you 60 over 700 divided by 640 over 700, if you use the same method we use that, is a ball down to 60, boil down to 60 over 640. And if you now, here, if you, the other side of the equation, B0 plus B1, you know, yes, even though you have considered obesity, but the value of obesity is 0 here. That is no, is 0. So it will still cancel out this. So eventually it will give you B0 is this. Look at it, obesity is equal to 0, 60 over 640, it will give you the logarithm of it, will give you the. You see there's a difference between both of them. This one is not intercept when you are not considering
x at all.
X. But this is the intercept when you are considering X. So the first one is intercept when the obesity is not there. This second one is intercept when the obesity is there. Then let's now look at the value of the beta when the obesity is yes. Because obesity is being considered doesn't mean that for everybody there, they have obesity. And that is the scenario, those ones that don't have obesity. That is the scenario here. But here now, they not have the obesity. If you now come, out of the 300 that have obesity, 460 have the cardiovascular disease, the outcome. And you will say that the prevalence, the probability is 446 over 300. But we are considering the heart, which is the 446 over 300 divided by 254 over 300. If you follow what we did the other time, it ends up with 46 over 254. And in this side of the equation, you will see that X has value because the obesity is here is 1. So you now put it there. So when you now calculate from the table and look at the heart is minus 1.709. So this minus 1.709 is addition of B0, beta 0, and beta 1. So of course you have already calculated beta 0 here. If you substitute for the value of beta 0, you put it here, you'll be able to know beta 1. So you now move this one to this side, and beta 1 will now be 0.658. Now, the result you have just gotten now is you have gotten the two things you need. The beta, when the obesity is there now, the beta 0 and beta 1. The beta 0 is minus 2.367. Beta 1 is 0.658. If you were to be linear regression, that is the regression coefficient. No, it's still regression coefficient here. The interpretation is different. I've already said it before. If you were to be linear regression, that is the change in the value of y per unit change in value of x. But here, it's not the change in value of y. It's change in the value of logit y. Thank you. That is logit y. Log hot is called logit. It's a very change in value of log hot of y by unit change in value of x. It's not the actual value. So it's difficult, it doesn't make meaning. So the intelligent people now say, okay, since we've gone ahead, what brought us to this place is trying to find a solution. We want to do logarithm. Why not, if for us to be able to have meaningful conclusion, why not go and do anti-logarithm to reverse the output back to the format. So anti-log is also called exponential. If you calculate the anti-log of each of them, can you see of each of these are the anti-log. These are the anti-log. And the anti-log now, let's just consider this beta 1, people that have obesity, the obesity now. Is telling you this beta 1, the anti-log, 1.93, is telling you that those people is the hot ratio. If you remember, this beta 1 is hot, increase change in the hot of obesity, per unit change, change in the hot of the cardiovascular disease per unit change in obesity. For one person that have obesity, change in the hot of the outcome. So now when you calculate the anti-log, which is the exponential, is the odds ratio. That is the odds ratio. The odds ratio means that how many times. So you know anything you write is over 1. So you can always say 1.93 over 1. What it's telling you is that if the odds of having cardiovascular disease is 1.93, the odds of not having it will be 1. Or if the odds of not having it is 1, the odds of having it will be 1.93. So odds ratio, you divide the two odds. So the numerator is not higher than the denominator. It's telling you that the people that have obesity, they are 1.393 more likely to develop cardiovascular disease. Because if you say 193 over 1, what is telling you that is if the people that don't have obesity, their odds of having cardiovascular disease is 1. The people that have obesity, their odds will be 1.93. So if you divide that 1.9, that shows that the people that have obesity, they are 1.93 times to have cardiovascular disease than people that don't have obesity. That's just it. And if you run it with the SPSS, it will give you an output like this. Maybe I can just even show you, share the output or let directly instead of paying even showing this. Let me just show you the output directly, because I still have it there. Let me just show you the SPSS. I see you can see now. This is the SPSS output. If you run this same thing we have calculated we have, you can see the first one is a block 0, the beginning. That block 0 is telling you that we are not considering any X now. It's only this. We are dealing with people that they just have cardiovascular disease. We don't want to know what are the factors. So, of course, look at it. If you look at it, it's a variable not in the equation. Obesity is not in this equation. Even though obesity is a factor, which you put there, they remove it from the equation. They now look at it, variable in the equation. Can you see now? And now say constant. The constant means beta 0. Can you see beta 0 minus 2.132? So if you calculate the antilog exponential, odd ratio is 0.119. And that was what, if you look at what we show in the other way, in another place, it's the same thing. Let me just show you, because it's good to move in between these two slides so that you can appreciate, okay, the same thing. It's just for me to move up. So look at what we calculated. Look at what we calculated. Can you see? 2 minus 2.132. It's the same thing we calculated. And that is what it brought up for us for that one. Now, if let me reshare. Yes. Now let's go to block 1 now. After we are through with that, block 1 means that it has put in the obesity now. Now, just go to the result. Look at the last table. You will see the result. Look at the beta 0 is minus 2, constant, minus 2.367. That is what we calculated in that place also. And the beta 1, which is for the obesity, is 0. Obesity is yes, is 0.658. Same thing we calculated. Now, if you look at the odd ratio, look at the odd ratio 1.932. So that is, so interpreting it. So what I want to explain also is how do you, when you run it like this, how do you interpret the result? You will see this beta is supposed to be the regression coefficient, because it doesn't make sense. Because what it just means that increase in the log, the beta just means increase in the odds of the outcome per unit increase in X. So, but if you now transform it to you do the antilog, that is exponential, it gives you the odd ratio. How many times the people that are exposed are more likely to have the outcome than the people that are not exposed? The only thing I want to also say here is that sometimes you will see the confidence interval. The confidence interval is 1.28 to 2.913. It does not cross 1. It's significant, because if, let's say, it crosses 1, maybe it's from 0 point something to 2.9 now. Know that for you to move from 0 point something, 1 is inclusive in between. It's not significant, because the meaning of the confidence interval is that though my odd ratio is 1.93, but in the population, I'm 95% confident that the real value of the odd ratio in the population will be lie between 1.28 to 2.9. Now, if it has included 1, that means that you know that when the odd ratio or relative risk is 1, it means that there's no association. So it's not significant, because it means that the risk is the same thing. 1 over 1 among the exposed and not exposed is the same. If the risk is the same, that shows that that factor is not a factor. If people that are exposed to a factor, they have the same disease at the same rate with people that are not exposed. That shows that is not, it's not that thing that is causing it, it's not a factor. It's neither protective or not causing it, because the risk is the same among both sides. But if the odd ratio is greater than 1, it means that the risk is higher among those factors exposed to the factor. But if it is less than 1, it means that the risk is lower among those exposed to the factor. That shows that the factor is protecting it. So here, the odd ratio, the confidence interval does not include 1, is significant. Now, what if you look at it, you also see the p-value there. You see something. You see p-value. You see odd ratio and confidence interval. On this table, you are having two inferential methods presented. No, there are two separate inferential methods, hypothesis testing and confidence interval. This odd ratio together with the confidence interval is confidence interval. This other one, you see what statistic, degree of freedom, and p-value is hypothesis testing. They are different. It is hypothesis testing that ends with p-value. It can be any test. It can be t-test, it can be chi-square, it can be ANOVA. Think of any test, end up with p-value. That is hypothesis testing. It's different from confidence interval. There are two separate methods of inferential statistics. And the third method is Bayesian method. But people don't use it. It has been there. Don't use it much. But the commonest one are hypothesis testing and confidence interval. But there are some, especially in medicine, if you want to publish in high impact journal like Lancet, they will not take p-value from you. They prefer confidence interval because they believe that that p-value does not have place in medicine. They said that it started from agricultural research in the early 19th, where they just dichotomized study into significant and not significant. So they believe that many people in medicine believe that it doesn't have place in medicine. So the confidence interval. So the software, they are programmed in such a way that it will, most of the time, it will give you both confidence interval and hypothesis testing. Just like if you are doing t-test, it's the same thing will give you. They give you the t with the p-value, that is hypothesis testing. Also give you confidence interval together with it. So it's now left for you to choose. You know, computer is garbage in, they don't know what you want. So that normally, if you are showing your result, you are showing both of them the repetition. But in an environment where people, they only know p-value, if you want to show your confidence, you still have to put the p-value, because some people, they don't see the p-value, they won't understand your result, they cannot interpret it, they will not know if it's significant or not. Whereas the p-value only tell you if it's significant or not. The confidence interval tells you if it is significant or not. In addition to that, it also tells you two other things. Now, it will give you the value, a particular value like the odd ratio now, it gives you a value, and also give you a range of value within which you can find the population value, which is the confidence interval. Can you see? So it gives you three information. It will give you a value, it quantifies the association for you. It quantifies it for you. Then it also gives you a range of, that's one. Two, it gives you a range of value within which you are 95% confident that you find the population value. The third one, it tells you if it's significant or not. And if it is significant or not, that's the only thing the hypothesis testing tells you. The p-value, that's the only thing it tells you if it's significant or not. But that also tells you that people may not know how to, it's knowing how to interpret it. But if it's significant with hypothesis testing, it will be significant with confidence interval, because somehow, the statistic has made it that this level of significance correspond with level of confidence. If you set your level of significance to be 0.05, that is, it has 0.05, you want to reject no hypothesis. That shows that your level of confidence is 95. Both of them add up to 100. That is, if you choose 5%, the confidence level is 95. So that is why it actually gives the same result. But whichever one you present, you are limited to the interpretation there. As you have said, the p-value gives you only one information, while confidence interval gives you three information, which include one of those, the only one that the p-value gives you also. So you see. So when you are presenting, it's a matter of, it was to be, people that know what they are doing. If you present confidence interval, there's no need for you to prove the p-value. Now, even when you want to put it, so sometimes now, when you present a people just put 0.0, the p-value, the odd ratio, and the confidence interval. But what of all this other one? Sometimes some people like me, I will allow it if you are coming to present to me as an examiner, I will allow you to give me all the information on that table. The reason is very simple. People can tell lie. People tell lie with statistics. Because many people want something to be significant. You can change any of these values. But those same people, they may not know the logic behind all this other one. So if you look at it now, if you have your result now, if you have maybe your what do I call your calculator or your Excel, you can calculate the antilog of 0.658. The antilog is the exponential. If you calculate it, it will give 1.932. Imagine somebody show this one and now change the odd ratio here because you want it to be significant or you want to change it for one reason or the other. If somebody now pick your beta and calculate the antilog, which is exponential, if it doesn't get the same result, that shows that you are telling lie. Now, this standard error, what does it mean? The standard error is for you to understand. You know, standard error tells you how precise your study is, your estimate. This beta is the standard error of this beta. This beta, if the standard error is very big, it shows that it's not so precise. If it's very small, it's precise. Now, if you put this standard error divided by the beta rather divided by the standard error, it follows normal distribution. They call it what statistics. It follows normal distribution. It's Z. It follows Z distribution. In some software like a P-info, maybe I don't know, maybe other like maybe the same thing with startup. It is Z that you Z it will give you. It will not give you. You will not write it. It's Z. Because when you divide beta by standard error, it follows normal distribution. But SPSS will square. If you square it, it follows chi-square. So this value, if you divide this beta now by this one and square it, it gives you this. So why, if you present all this, if somebody play with the result, someone that knows what is doing can pick a result and just try to find out if you are play with the result. Because if you, so the origin of all this one, if you divide the beta by standard error and square it, it gives you this 9.87 for the word statistics. And it's a chi-square. And since the degree of freedom is 1, if it's not going to be significant, if let's say the value now is less than, because the critical value for the degree of freedom 1 for chi-square, because this word is chi-square, the critical value for the degree of freedom 1 is 3.84. So if you now calculate it, is less than that, it will not be significant. And somebody has said that it's significant, you know that he has told lie. He has told lie. So that is just it. So it's just for you to understand some of those nitty-gritty. But in many occasions, people just present the p-value and this and go with it. So it now depends. If you are the examiner or the assessor, that's okay. I want you to present the whole thing. So there's reason for that, because people that know what they are doing. Because especially if they suspect that the person is telling lie, because many people tell lie very well with statistics. I think we stop here, and I want to entertain questions. If there's any question, I'm sure if you have questions, you might have chatted some. Okay, no chat. Any question? Oh, no question. Okay, so that shows that it's very, okay. Somebody thank you. Okay, somebody say thank you. That shows that it's said.
Thank you. I do have a question.
Okay, go on.
Please, how do you really? I thank you very much. I got the reporting system you talk about, but how do you write this thing down in words? If you want to express logistic regression report, how do you write it when you are describing in your results?
Okay, yes. How do you write it? Okay. Now, I think I said it. If I want to discuss that result, I will not say that those who were obese, were 2 times more likely to have cardiovascular disease, and it could be as high as, what is the upper limit of that? Let me show you. See the upper limit of the confidence interval. The upper limit is 3. Yes, I will not say it could be as high as 3 times. I will now quote the confidence, the odds ratio. I will now say 1.9293. You know, in 1.93, you approximate it as 2 times. Because instead of saying 1.93 times, because you can swear, because it's approximation, you can say because it's almost 2. That's why we say that those who are obese were 2 times more likely to have cardiovascular disease than those who that were not obese. Can you see now? They are 2 times more likely than those who are not obese. And it could be as high as 3 times. You now quote your odds ratio and the confidence interval, the way they are. So when you are quoting your odds ratio and confidence interval, you will not approximate, you now quote odds ratio 1.93 confidence interval from 95% confidence interval from 1 point something to 2.9. You quote it like that. But when you are expressing the sentence, you are free to approximate. So that, because it doesn't make sense when you say 1.9 times. So you are giving people a headache. So you better say 2 times. Because if it is 1.4 now, 1.3, you know that is, yeah, you can see if it's significant, you can see put it 1.4, since you cannot say 1 time. Even if you say 1 time, it doesn't make meaning because it's the same. It makes it the same. But once you are having something that is close to 2, why not approximate it? Even if it is 1.6, even 1.5, you can say 2 times. But once something is halfway, approximate it. Is that clear? Does that answer your question?
Yes, thank you, it's clear. Thank you.
Okay, that's good. Somebody asked question.
So what you have to state the method that is done by logistic regression. It's not important to state the method you use, the procedure. Because I've read that, so you can say that.
No, if you are stating your result, even in your methodology, it will have been there. Or if even the table you are interpreting from, your table of your result will have shown if it is simple logistic regression of this or multiple logistic regression of this. So the funniest thing about regression is that you say that regression of the outcome on the factors. If you were here for the lecture or you listen to the lecture on linear regression, I think if you have not, okay, Dr. Ogundeji, maybe you even subscribe, and you are like, maybe if you have listened to the meaning of regression, regressors mean going back. You are moving from cause from effect to cause. So that's why when you are stating your table, you say table of your table, the title of your table will be regression, simple or multiple regression of the outcome. If I want to state for it, I will not say for this one now. I'll say the regression of cardiovascular cardiovascular disease on associated factor. If there's already there are plenty. But if it's only one, I want to say on obesity, regression of cardiovascular disease on obesity. It shows that the outcome is cardiovascular disease. The obesity is the factor. So most of the time, if there are many factors you have done there, that's a regression of cardiovascular disease on predictor or determinant or associated factors. So if you look at it now, it's carrying. The table is very funny. You will not see, apart from the title, you will not see anything that relates to a cardiovascular disease there. Everything you see there are the names of the exposure variables. Yes. Okay. Some question here. Somebody saying, please, can you convert odds ratio to this ratio? Yes. There's a formula for that, and I've given it also. Please, well, maybe the person, well, you may be around, but maybe when we talk about measure of association, in fact, this is 2 lectures now. We talk about odds ratio and relativity. There's a formula there that I gave out that is convert. You go and get the material. Just get the material you see. Go and listen to that, or you subscribe, you get the material. Maybe I just show you the formula is there. Because the risk ratio is the real issue, is the real measure of risk. Odds ratio is a proxy. It's a proxy, it's approximate. And most time, what you see in literature is odds ratio because of the limited, because of the problem of the study, because it is easier to carry out a study that will generate odds ratio. And apart from that, even when you even carry out a study that can generate relative risk. Like the statistical package, the type of analysis you use is odds ratio, it's more universal you use. So because of that, they report odds ratio more than relative risk. So in a situation where maybe you want to do all those economic evaluation, or you want to look at, a project, you want to actually evaluate a project, a particular program or project, you actually want to have the accurate measure of the risk. You can convert the odds ratio to the risk. No, I said it there that when risk is greater than 1, the value of odds ratio is usually bigger than relative risk ratio. So it will amplify it. So the risk is giving you is overestimating. Yes, it's overestimated. So odds ratio, when risk is greater than 1, the risk is estimated if you use odds ratio. But if the risk is less than 1, is underestimated. The value is underestimated. So it's still the same thing. Because if you underestimate it, it's still overestimating that thing, because when the risk is less than 1, it means that thing is protective. Is protective. That particular thing is protective. So if by telling you the value is lower, it's telling you it's amplified, that it gives the impression that it's protecting more, but it's not actually protecting also that. So somehow the value of this is different, risk ratio is different from odds ratio. You can convert it. So I will show you. I think that slide where I show the formula. I think it's on the, sorry. Let me just look for it. Yes, any other question? I have a question I'm still answering. Somebody has a question, I will come and attend to it. I'm coming. Let me just quickly show that slide. That slide, that's a measure of association, yes. Yes, this one. Yes, this is it. So can the person see? To convert odds ratio to relative risk, this is the formula. R is equal to R OR over 1 minus P0 plus P0 times OR, where P0 is the sample probability of the outcome. So very straightforward. You can convert it. So let me quickly answer the other question. Yes. What is the relationship between prevalence and log odd, or is there a no relationship? We have already, the prevalence is the probability. When you say probability is the prevalence. So how the relationship is that it's like acid. The odds is prevalence over 1 minus prevalence. Because prevalence is probability. It's just the probability, you are just calling it prevalent. You are expressing percentage. So odds is prevalence over 1 minus prevalent. Logarithm of it is the log odd, which is the logit. So that's the relationship. So I think there's a slide also that, because I think I have emphasized that particular thing before. Where am I? Okay. There's a slide, in our slide, there's a place. Yes. Look at this slide. To buttress that point. This first slide here is showing the distribution of prevalence. You know, when you say prevalence, that is proportion of something. If you say prevalence of something is 30, the prevalence of not having it is 70. It's followed by binomial. So if you plot it, if you take sample many times, it follows normal distribution. Can you see, if you remember, when does it peak? If you follow the highest frequency is 0.5, 50%. I think I've demonstrated that before. When I multiply 1 times 9, 2 times 8, 3 times 7, 4 times 6, 5 times 5, 6 times 4, 7 times 3, 2 times 8 times 2, 9 times 1. If you look at the value of all these things I just said now, it will begin to increase, reach 5. If you say 9 times 1 is 9, 2 times 8. The thing there is that you are splitting 10 into 2. You can add those two numbers to form 10. If you have 10, you say 9 and 1. 9 times 1, it gives you 9. If you split the 10 into 2 times 8, 2 and 8, it gives you 16. 16 is greater than 9. If you split into 7 and 3, 7 times 3, 3 times 7 rather, it gives you 21. If you split into 4 and 6, 6 times 4, 24. And you see it's increasing. You split into 5 and 5, 5 times 5, 25. If you now say, you know you have already done 1 times 9, when you now come back to 6 times 4, you're going back. It will be going down. 6 times 4. If 4 times 6 is 24. 6 times 4 is 24. So 7 times 3 is 21. Until you go back to 9 times 1, it gives you 1. So you see the highest is 5. So it's just like if you toss a coin and you know the coin has two sides, 50-50, 50%, 50%. You say what's the probability of it being hit? It says 7.5, 50%. If I give you a coin to toss 20 times now, you can be sure that even 15 or 80 times it can be hit. It may not give you that your 50-50. It doesn't mean that if you toss it 20 times, it give you 10 head, 10 tail. Before you can have that 50-50, you have to toss it thousands or millions of times. If you toss it millions of times, it will be, the answer will be around approximately 50-50. So that is where it is when the sample size is very large. So when, can you see now, the highest prevalence here is 50. Can you see? The 0.2, 0.4, this was 0.6, the middle is 0, the highest is 0.5. So when you plot, this is probability. When you plot it, it follows normal distribution also. Especially when the sample size is high, it give you this. Now, if you calculate the odd, that is P probability over 1 minus probability, it gives you this. It's skewed. So this is what they wanted to use instead of P. See, we know that the problem with probability, the binomial, is that it gives you two poles. Either you are there or not. So we are looking, it's bounded in between 0 and 1, or in between 0 and 100%. It cannot go beyond 100%. It cannot go below 0. So that is the problem. And we are looking for something for us to, can give us leverage to have many values outside that range. So when you now calculate, how do you do? Transform it, you can't change it to odd. That is P over 1 minus P. You know, odd is said is ranging from 0 to infinity, while probability ranges from 0 to 1. But you can say that odd is more flexible, that at least from 0 to infinity. But the problem that is skewed, while probability here is normally distributed here, at least for binomial, if you have large sample size, but here is skewed. When you calculate the odd, it's skewed. So in trying to solve our problem, it has given us a wider range, but it's skewed. That is why intelligent people, they didn't stop there. And that's okay. Now let's calculate the logarithm of this odd. The logarithm of odd now solve the solution, give us the solution, solve the problem. Itself also is normally distributed. You can see the middle of that one is 0. The middle of this probability is 1. You know why it's like that? You know that when the probability is 0.5, is 0.5. Sorry, the middle for this one is 0.5, not 1. It's 0.5 for probability. Why is 0 for log odd? You know that when the probability is 0.5, that is, that's travel halfway from 0 to, no, the halfway from 0 to 1 is 0.5. The odd will be 1. When probability is 0.5, always 1. How do you know? P all over 1 minus P. If probability P is 0.5, 0.5 all over 1 minus P is 0.5. It will give you 0.5 all over 0.5, which is 1. And the logarithm of 1, the logarithm of 1 is 0. Logarithm of 1 is 0. But any logarithm of anything is 0 point something would be negative. Logarithm of anything greater than 1 it will be positive. So anything, logarithm of anything less than 1 will be negative. Logarithm of anything greater than 1 will be positive. So, and you now have from infinity to infinity. So the log odd negative side is to infinity. Log the positive side is to infinity. Can you see? It has wide range. It's no more from 0 to infinity. It's from infinity to infinity. And you see, infinity on the negative side to infinity on the positive side, and it's normally distributed. It has solved the problem. Can you see that it's not bounded? This one is normally distributed, is bounded. This one is not so, it's not bounded, but you want bounded on one side, it's not bounded on the other side. It's open on one side, the other one is bounded, but it's skewed. But this one is not bounded, infinity to infinity, and it's normally distributed. That is why it was used. So if they ask you, that is the relationship. So it's the relationship. So you convert probability to odd and convert odd to log odd to solve the problem. I think, I don't know if that one has answered your question to a certain extent.
Yes, sir.
Yeah. Yes, another one. Okay, there's no question. That would be great. So if you have, you can chat it, but okay, no problem. So thank you. I think I can pause the video